We're going to recap a couple things from a previous day's lesson. I know I already have it written down, but I'll just talk you through it for the next minute or so. If we construct a polynomial with 4 terms for the function natural log of x centered at 1, all of the derivatives for the first 5, the first 4 derivatives plus the actual value of the natural log of 1 are listed in that thought bubble over on the right. So then we write out the polynomial. Notice that 0 we can't count as a term, so we have to go to 5 terms, so to speak, so that we can get 4 terms listed for the natural log of x in our polynomial here. And then I wrote the general term in blue over on the right. So that's a polynomial with 4 terms for the function f of x equals natural log of x, because each term in a Taylor series is the nth derivative evaluated at a point, or the center point, times x minus c to the n over n factorial. So that is each term in the series. One thing that you might want to note is that 4 factorial is really 4 times 6. And so that's why we can cancel off the 6's and get 4 in the denominator. 3 factorial is really 3 times 2, so that's why we can cancel off the 2's and get the 3 in the denominator. And that's why there's an n in the denominator instead of an n factorial, because all of these derivatives end up with n minus 1 factorial as the numerator. Problem 2, construct a polynomial with the following information. We know that the center is at 2 because it gives us all this information at f of 2, f prime of 2, and so on. And then we know the values of those things, so we can write our polynomial as is stated in red. Let's move along to problem 3. Write the Maclaurin polynomial with 5 terms for f of x equals e to the x along with the general term. So we've written the polynomial for e to the x. The general term, if I wanted to write the Maclaurin series for that, I would probably write it as a summation, so n equals 0 to infinity of x to the n over n factorial. Now let's use the polynomial from 3a to generate a polynomial for g of x equals 1 plus e to the ix. Because there's a 1 there, I'm going to put the 1 in front, and I'll make that green so that it's pretty obvious. But then after that, we have this e to the ix. So essentially what I'm going to do is I'm going to take my Taylor series, or my Maclaurin series for e to the x, and I'm going to replace x with ix. So that basically means every term in e to the x gets replaced with, every time there's an x that shows up, an ix is going to take its place. So 1 plus ix plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial, and so on. So I will rewrite that as 1 plus 1 plus ix plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial plus I to the 4th x to the 4th over 4 factorial, and so on. One thing that's worth remembering, something from Algebra 2, is the rules about I. So I squared equals -1, I cubed equals -I to the 4th is back to 1. And so what we have here is essentially a circle of I. So if we have I to the 5th, we circle back to I to the 1st, which is I to the 6th is -1, and so on. So that's something that's worth remembering in order to do this problem. Now to find g of pi, notice that g of pi is going to be 1 plus e to the I pi. So I've pre-written a lot of this in order to save ourselves some time, but I have the 1 from the problem that I circled in green. I wrote that in green. And then I've kind of rewritten everything in some sort of alternating red-green pattern from our original problem. And now I've rearranged g of x with all of the reds and all of the blues kind of put together. And then I'll put the +1 that's in green at the end right now instead of at the beginning. And so what we have here is we have this stuff in red, which someone that is relatively astute might recognize is actually cosine of x. And then we have this stuff in blue that somebody that's kind of astute might recognize as I times sine of x. And then we have this +1. So that's what's going on. I'm going to stop writing in alternating colors now. But now what I want to do is I want to take this and I want to sub in pi because that's what I am trying to find. So g of pi is cosine of pi plus I times sine of pi plus 1. Cosine of pi is -1. I times sine of pi is I times 0, so that's 0. And then plus 1. So g of pi is actually 0. That means since g of pi was e to the I pi plus 1, we know that e to the I pi plus 1 is 0, which is actually one of the more fundamental, crazy, intense things in math, that 5 of the most important or valuable constants in all of math are related in one equation with nothing else. So e to the I pi plus 1 equals 0. And the reason that we know this, which is often called Euler's identity, one of the reasons why we know this is because we can use Taylor series or Maclaurin series to prove it. So we can use series, and if we actually substituted in pi for x into all of this stuff in red and all of this stuff in blue, and we did it infinitely, we would find out that the red stuff would become 1 or -1. The blue stuff would become 0. Obviously, that would go off to infinity, but that's what those values converge to, and that's because they are cosine and I times sine. All right, now let's move along to some examples that get to error in Taylor polynomials and Maclaurin polynomials. So example 1a, use the third degree Taylor polynomial for natural log of x centered at 1 to approximate the value of natural log of 1.1. So we could actually approximate values at a specific point. This is something that we talked about because this is, once again, really an extension of tangent lines beyond just a linear format. So this is going to be a third degree polynomial. And when I copied this from the front, obviously the squared and the cube didn't get copied, my fault. But if I'm going to approximate natural log of 1.1, what I will do is I will substitute 1.1 in everywhere there's an x. So I end up with 0.1 plus 0.1 squared over 2. I'm sorry, minus 0.1 squared over 2 plus 0.1 cubed over 3. And that ends up equaling 1/10 minus 1/200th plus 1/3000th, which is equal to 143 over 1500. And no, I do not know that off the top of my head. I'm doing this in the interest of not boring you to tears with trying to find all that in my head. So now 1b is what is the error of this approximation? Well, before we get into that, let's just remind ourselves that natural log of x centered at 1, if we did the ratio test, limit as n approaches infinity. I'll do this in a different color so it's easier to see. If I did the ratio test on the general term, the -1 to the n plus 1 doesn't really matter. So I have x minus 1 to the n plus 1 over n plus 1 times n over x minus 1 to the nth power. Sorry, that's all over on the side, but that simplifies to the limit as n goes to infinity of x minus 1 to the n over n plus 1. Sorry, not x minus 1 to the n, x minus 1 times n. And as that goes to infinity, I end up with x minus 1. So that must be less than 1, since that's the rule on the ratio test. So x minus 1 is between 1 and -1, which means x is between 0 and 2. If I substitute in 2 to my general term and look at its convergence, it does work. If I substitute in 0, that doesn't work because I can't sub in 0 to the denominator of anything. So natural log converges from 0 to 2 if I center the polynomial at 1. So because I'm doing natural log of 1.1, if I have an infinite number of terms, this will actually converge to the correct value. If I was trying to approximate natural log of 2.1, I could not have my polynomial centered at 1 and actually get an answer that is close to what's correct. So the error of this approximation, we'll come back to that in a second. So this can be used, or we can describe this using the remainder, which is defined as follows. So we have some function, and that is equal to the polynomial, which is our approximate value. And then we have some remainder that is obviously missing. So the exact value of the function, so in this case, natural log of x, is equal to the Taylor polynomial that represents the natural log of x, and then whatever it's off by, the remainder, because we have some sort of remainder that will converge to the natural log of x as we move along. So if I solve for the remainder is equal to the function value minus the polynomial. And we call the absolute value of this remainder the error approximation. So the remainder, or the error, is pretty much equal to this function value minus the polynomial. And we take the absolute value of those to consider that the error. This is called Taylor's theorem. So Taylor's theorem, I wrote a lot of this out in the interest of saving time in the video. But if we have some differentiable function that's at least differentiable through one more term than the polynomial that we have, then there exists a z between x and c such that the following is true. We have this whole polynomial, I wrote that in black, and then plus the remainder. So the remainder is in red. This z, this random number z, actually is the exact value that when you plug it into the derivative, the n plus 1th derivative, that exactly equals the remainder. So there's some value between x and c. So x is whatever the function is. Z is some value in between. And then usually c, our center, is bigger than or less than x or whatever. So we could have c less than or equal to z less than or equal to x. It just depends on whether your x is bigger than or less than where your center is at that particular time. So if your center is smaller than the x value you're plugging in, you're going to look at this situation. If your center is bigger than the x value that you're plugging in. You're looking at this situation. But in either case, there's some value z that exactly when plugged into the n plus first derivative equals the value of the remainder. So that's called the Lagrange formula, or the Lagrange form of the remainder. Now, we often cannot find that z. That z is very hard to find. But what we can do is we can just make sure that we maximize the possible error so that we know that it's at most this far away. And so what we do is we take a, some value a, and we try to maximize the derivative in this particular equation. So the remainder must be less than or equal to the maximum derivative, the maximum n plus first derivative over n plus 1 factorial times x minus c to the n plus 1. So notice, though, that this error term is always less than or equal to the next term. So that ends up making this practically pretty nice to find. All we have to do is take the next term in the polynomial. So if we have a fifth degree polynomial, we just look at the sixth degree term, or in a sine or cosine case, the seventh degree, 2 away, whatever the next non-zero term is. And that's the maximum error that we have, as long as we replace what the derivative is at c with the biggest possible derivative that we can have. So here it is written a little cleaner. I stole it from a website. I gave credit to the website that I stole it to. And then I replaced all the letters that the website had with the letters that we had. But this is a nice clean way of writing it with a summation notation and everything else. So now let's go back to the original problem. What is the error in this approximation? This is something you did last year in honors pre-calculus. So if we want the remainder of the third degree polynomial, we look at the fourth term. So the fourth term, remember, is going to be x minus 1 to the fourth over 4. Now, the reason why that works is the maximum possible derivative of natural log of x between 1 and 1.1, the maximum possible fourth derivative, is 6 over x to the fourth. If I plug in 1, then I get 6. Well, it's actually negative 6, but I'm taking an absolute value essentially. So I get negative 6, but if I plug in anything bigger than 1, then this number gets smaller. So the maximum possible derivative between 1 and 1.1 for x, I sub in 1, and that's the maximum possible derivative. So the next term, maximum possible derivative, is negative 6 times x minus 1 to the fourth over 4 factorial. Notice that negative 6 over 4 factorial ends up just having a 4 in the denominator, which is exactly the next term. But again, if the derivative could possibly be bigger, then we would have to take that into account. And then I have 1.1 minus 1 to the fourth power. So that's 0.1 to the fourth power over 4, which is 0.000025. So this 143 over 1500 is off by at most 0.000025. It's actually off by less than that, but this is the maximum possible situation of being wrong. So the remainder is less than or equal to that thing. All right, we'll do a bunch of examples now. E to the x is 1 plus x squared over 2 factorial, because it tells us that it wants a quadratic in the problem. So if I want to find the value of e, notice that e, remember, converges from negative infinity to infinity, so I don't have a problem with this. I'm just going to substitute in 1 because I want e to the 1. And my approximation gives me 2.5 at the quadratic level. So the second degree Taylor or Maclaurin polynomial gives me 2.5, and I know that e is approximately 2.71828 or so on. So we know that for real it's off by about 0.21, a little bit more than 0.21. But let's find the Taylor remainder. So R of 2 is the next term. So that's the maximum derivative, which I'm now going to label M. So the maximum derivative times x minus c, which in this case is x minus 0, to the third over 3 factorial. Now, what is the maximum derivative of e to the x at the third level? That's still e to the x. So the maximum possible derivative between 0 and 1 is actually e. But instead, since e is kind of nasty to calculate, I'm just going to notice that e to the 1 is less than 3, and 3 is a pretty decent bound for that. So I'm going to replace m with 3. Let's just call the maximum possible derivative in this particular case 3. So I have 3 times x cubed over 3 factorial. This is going to be what I'm calling r sub 2, which is less than or equal to this. So that's the same thing as x cubed over 2, which is the same thing as 1/2 when I substitute in 1. So my maximum remainder is 1/2, which is correct because e is definitely between 2.5 and 3. Now, if I wanted to write an interval that e is definitely in the interval 2.5 to 3. And we know that it's about 2.71828. Okay, construct a third degree Maclaurin polynomial for sine to approximate sine of 0.1. Use Taylor's theorem after that. So 0.1 minus 0.1 to the third over 3 factorial, which is 6. So that is 1/10 minus 0.001 over 6, which is 599 over 6,000. Let's find what the remainder is. So the remainder, I have to go to the next term. So the maximum possible derivative of the next term times x to the 5th over 5 factorial. Now, the next term is the derivative of sine is either going to be sine or cosine or negative sine or negative cosine. The absolute value of the maximum derivative of those things is 1. So we'll make m equal to 1. And go from there. So in this situation, x is 0.1. So I have 0.1 to the 5th over 5 factorial. So my remainder is 8.3 repeating times 10 to the negative 8th. So that's my maximum possible remainder. If I wanted the exact value of the error, I calculated that. So that's sine of 0.1 minus what my approximation was, and that is 8.3313494825 times 10 to the negative 8th. So notice that in this case, my remainder calculation using Taylor's theorem is only very slightly bigger than the actual error that I had. And notice the error is really small. I have example 4 and example 5 written out because I've recorded it about 4 times and it keeps on not having any audio, so I'm going to try this one already. Example 4 is a lot like example 3. So if you look at example 3, we have a sine and a cosine. Basically, the maximum possible derivative of sine and cosine, no matter what it is going to be 1. That's a pretty easy way to calculate it. We probably could figure out something that's a little bit smaller, maybe for sine, but it really wasn't that important. So m, maximum derivative is 1. I take m and substitute 1 in, and then I put 0.3 in for x, and I figure out that my remainder is 0.00000010125. If I find the exact value of it, it's 0.00010100874393997, which is smaller than what we said our maximum possible remainder is, which is good. It's also pretty close. So now, what if I have to determine the degree of a Maclaurin polynomial required for the error to be less than 0.0001. So in that case, I'm basically working backwards. So what I want to do is I want to find the n such that when I have the maximum derivative times x to the n plus 1 over n plus 1 factorial, that ends up being less than 0.0001. Now notice that 0.6, when I sub it in for e, or e to the 0.6, I'll get some value, but it's not that easy to get without a calculator. I probably could get it and I could determine it, but it's pretty straightforward and safe to say that e to the 0.6 is less than e to the 1, which is less than 3. So I will replace m with 3. And then I just need that to be less than 0.0001. So I divide both sides by 3, and I get this right here. So now I need to figure out what n that I sub in gives me a value of this this next term, so to speak, less than 0.00003 repeating. I tried several things. 0.6 to the 5th over 5 factorial. That's not quite less than what I need it to be less than. 0.6 to the 6th over 6 factorial is closer, but still not quite. It's just slightly too big. 0.6 to the 7th over 7 factorial is our winner. So that is the degree of the degree of the Maclaurin polynomial is actually a 6-degree polynomial, because when I substitute in n equals 6, I get these 7s here. So the next term would be the 7th term, or the 7th degree. And so then as a result, my 6th degree polynomial will be the winner, where my error is less than 0.0001, which means that this is less than 0.00003 repeating. So this is my first situation where I get that, and therefore the 6th degree polynomial is uh, the degree of the Maclaurin polynomial that is required for the error to be less than 0.0001. One last reminder, just to summarize what's going on, I want to find the maximum possible error. I mean, the maximum possible error that I'm willing to live with, basically. I let the maximum possible derivative go into the next term. So it looks complicated with all of these c's and z's and x's and everything. But really, I just take whatever the polynomial is. So let's say I have a 5th degree polynomial. I look at the next term. So it'd be either the 6th degree or 7th degree or whatever the next degree is in the polynomial or in the series. And then I maximize the derivative value there between, just for e, if I'm like at e at 0.4, I just say, let's maximize it, make uh, it's definitely less than 3. And then I sub that in and figure out what the error is, or figure out what my n is that would keep it under the required error.